Good morning, ladies and gentlemen. My name is Massimo Celidonio and I am a researcher at Fondazione Bordoni, an Italian research center operating in the field of ICT and energy. The object of my presentation is the Edison project, which has the goal to develop and test an enhanced energy-saving solution for lighting network infrastructures suitable for public and private buildings, using ICT devices as well as an innovative architecture based on a centralized DC power supply. The project is partially funded by European Commission in the framework of FP7 ICT PSP program. In this slide is reported a summary of this presentation. First of all, I will provide some general information about the Edison project and consortium. It will follow a brief description of the Edison goals and its architecture, which includes the lighting network infrastructure, ICT components, and the data communication link. Benefit of the proposed platform will be also analyzed. Finally, some preliminary results carried out in pilot implementation will be reported and analyzed. The presentation will conclude with some final remarks. As I mentioned before, Edison, which stands for Energy Distribution Infrastructure for SSL Operative Networks, is operating in the framework of the European Call ICT PSP 2011-5 of the FP7 program, specifically in the theme 1.2 dealing with ICT for energy efficiency in public buildings. The consortium is composed by 14 European partners belonging to 5 countries that are Northern Ireland, Belgium, Italy, Romania, and Greece, and involves SMEs, universities, municipalities, and scientific non-profit organizations. Fondazione Bordoni is the coordinator and the technical manager of the project. Have been planned and realized 12 pilot implementations in schools, municipalities, hospitals, museums, located in 3 out of the 5 countries mentioned before. More information about the project and the pilots can be obtained at the project website here indicated. So, which is the Edison idea? Edison intends to suggest an innovative smart lighting platform based on a centralized DC power supply architecture to replace the actual AC systems in order to realize a substantial reduction of energy consumption. In addition, thanks to the use of ICT components such as sensors, smart meters, microcontroller cards, etc., a further significant reduction of energy consumption is guaranteed. In total, a reduction of about 70–80% of the current lighting infrastructure using fluorescent lights is expected. As a consequence of energy savings, we have also a relevant reduction of CO2 gas emissions in atmosphere, providing an effective contribution towards the achievements of the Lisbon objectives in the 2020 initiative. In this slide, we can see the architecture of the Edison platform. As it is evidenced, the platform is managed by a supervision center that can be a simple PC, and powered and controlled by a CPC, which stands for Central Power Control, and can communicate with the supervision center by power line modems or wireless LAN. As you can see, the CPC can be fed by the 48-volt DC provided by renewable energy sources, such as photovoltaic panels, or, in alternative, directly by the AC power line of the utility network, opportunity converted at 48-volt DC. The CPC is linked by the existing lighting network with the remote stations, or RS. which are in charge to manage the single lighting sections. For example, or more rooms, including, apart from the LED lights, also sensors and actuators. With this architecture, Edison combines fine-grained sensor and control technologies with a low-voltage DC-powered network for highly efficient LED lights to realize what we called a Smart Energy Platform, or SEP. The Edison architecture can be implemented in new installations, but can also be used for retrofitting existing lighting infrastructures. In this latter case, Edison has been designed to work in 3 different configurations. The first reference model addresses plants where the lighting infrastructure is separated from the EMF infrastructure, and a single electrical switchboard panel controls the overall electrical network. The second reference model addresses plants where the separation of the lighting and EMF infrastructures is not available everywhere, but it is performed locally. It means that a master electrical switchboard panel controls local slave panels. And finally, the third reference model addresses plants where the lighting infrastructure operates with a relay system. Edison, according to IEEE standard body, can be considered as a SELV, that is a separated safety extra low voltage system, as it is an electrical system in which the voltage do not exceed 50 volts DC under normal conditions and under single fault conditions, including earth faults in other circuits. A SELV system ensures a high level of safety against the risk of electric shock, both direct and indirect contacts. In addition, Edison platform makes available a data communication network on the existing power lines, also by using the third wire, the earth wire, of the common lighting power distribution network. Not necessary to power in DC, as well as it allows to directly use any renewable energy supply system, for example PV system, due to the native DC proposed platform. Going back to the components necessary to implement the platform, in this slide is shown an example of CPC implemented by the pilot in the University of Brussels. As you can see, it includes a smart metering system, a AC-DC converter, that in this case is internal to the CPC, because no renewable source is available to power the system, and some ICT and data communication devices. The resulting wired infrastructure linked to the CPC is an integrated power line digital network that we have called Power LAN. The remote station consists of 2 modules: a data communication remote control module to collect data from sensors, alarms, metering devices, etc., and to send commands to actuators to the lighting network, and a dimming module that is telecontrolled by the supervision center to switch on off the lamps or dimming them if necessary. The RS is allowed to operate in automatic or manual mode. In manual mode, the RS is disabled, and lamps are switched on-off manually and locally, as usual. The Edison Smart Metering System combines automatic data collection and online monitoring, reporting, and alarming. It is based on a smart meter able to transmit data to a supervision center, a data concentrator that collects data from the electricity utility meters via wire or wireless network, and a dedicated software tool able to control and monitoring the energy consumption, reporting several graphical numeric outputs, such as the total electricity consumption and the total CO2 produced saved since start of measurements. The Edison platform is developed with a top-down approach, allowing the collection of data using wired or wireless connections between CPC and RS, as well as RS and sensors actuators. Several information are exchanged among these elements, such as sensor status, peak energy consumption, current energy consumption, etc. Data communication between RS and sensors actuators is performed in an analogical way, using the data wires, that are the earth and negative wires of the lighting section. Data exchange between CPC and RS can be performed through a standard LIN interface, or, alternatively, using RS-485 or USB connections, depending on the specific arrangement of two devices inside the infrastructure. The communication between CPC and Supervision Center is carried out through a power line modems or wireless LAN, using Ethernet interface and IP protocol. To validate the Edison platform, 12 pilot implementations are currently running in 3 European countries. In this slide, I have reported the preliminary results carried out in one of them. The pilot has been installed by an area of the restaurant of the University of Brussels and includes 100 lighting points with a total power of 700 watts and 18 presence sensors. The graphs shows electricity consumption data registered during 5 days in 2 equivalent areas, both equipped with LED lamps, one with the Edison platform active and the other one without Edison. And from the analysis of these results, an energy saving of about 30% has been noticed. More details of the test are reported in this slide, where it is highlighted the test duration, the real energy consumptions, and relative gain for each of the 5 test days. Of course, we obtained the reduction of energy consumption thanks to the usage of presence sensors, but also by the implementation of DC centralized power supply. According to the operativity of the university restaurant, it is possible to estimate a yearly energy saving of about 500 kW per hour, corresponding to a reduction of 110 kilograms of CO2 gas emissions in atmosphere. In conclusion, some final remarks. The smart light infrastructure we suggest offers increasing flexibility, reliability, and opportunities to create comfortable, safe, and sustainable environments. In fact, being the proposed lighting power supply infrastructure a DC extra low voltage lighting power distribution network, and specifically a serve system, it makes possible quick and safer installation of lighting fixtures and other low-voltage devices. Operating in DC, it facilitates the direct connection and efficient use of alternative native DC energy sources. Reduces energy consumption through the synergy between LED lamps and sensors and control devices, estimated up to a maximum level of 80%. Contributes to a more environmentally sustainable energy policy, reducing CO2 gas emissions and leading to a global level in the fight against climate change. Okay, that's all. Thank you for your attention. For any question, please contact me at the indicated email.